All right, so likely in this lesson, I'm going to rough things up a bit. Content's going to get maybe a little bit more difficult, but if you stick with it, we can work through it. So let us look at logarithms differently. So we're going to consider the function, and it's an exponential function, y is equal to 2 to the power of x. So the base is 2. The inverse function of such a beast is going to be x is equal to 2 to the power of y. So really with an inverse function, all we have to do is switch the x's and y's. Now the problem with that form right there, on the right-hand highlighted equation, is that y isn't isolated. It is as an exponent. So how do we bring an unknown exponent down? Well, to find the inverse function, we would have to use the logarithms. So just like dividing is the inverse of multiplication, logarithms are going to be the inverse of exponents. Really, really powerful stuff. Naturally, when solving equations where the exponents are unknown or you want to isolate your exponent, you have to employ logarithms to solve. So let's just look at two functions. I did some of the legwork here, and I know that you can do this legwork ahead of time too. Just for speed, we're going to graph an exponential functions, and we're going to take a look at two exponential functions. The case 1, and this would be case 1. Case 1 is where our base is between 0 and 1. So, for example, the example that I'm going to be using is y is equal to 1/2 to the power of x. On the right-hand side, case 2, I will call this, is where our base is greater than 1. So, for example, y is equal to 2 to the power of x. So again, our base has to be positive, but I'm going to take a look at two cases. One where it's stuck between 0 and 1, the other one where it's greater than 1. So I'm going to ask you to take some time to graph this example and this example. So press pause, get started. All right, welcome back. So my whole goal is I'm going to graph the exponent functions. And I'm hoping that you've graphed that. Y is equal to 1/2 x will be shaped like this. And you are probably able to conclude that y is equal to 1/2 x will have a horizontal asymptote at y is equal to 0. That is, as x goes towards positive infinity, the y values will get very, very close to 0. On the other hand, this function here, y is equal to 2 to the power of x, is going to have this kind of look about it. Right? I'm going to make my points, right? That was -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4. So now I've graphed my exponential functions. So I'm going to graph the inverse of these functions. So how do I graph inverse? Now recall that I could give you any function, and you could graph the inverse simply by reflecting it about the identity line y is equal to x. And wouldn't you know, I have given you this identity line on our graph, y is equal to x. So I'm going to switch to purple. I'm going to work off this graph over here. I'm going to be moving this point. This point was -2, 4. So that becomes 4, -2. -1, 2 becomes 2, -1. 0, 0, 1 becomes 1, 0. Continue on. 1/2 becomes 1/2, 1. We can go to 2, 1/4 to 1/4, 2. And what we see is that this is the logarithmic, or this is the inverse function of my exponential. Now, since we had a horizontal asymptote for my exponential at y is equal to 0, this turns into a vertical asymptote for the inverse. Now, my vertical asymptote here will be x is equal to 0. Weird, right? So what is the equation of my inverse function? Well, now y would be equal to log base 1/2 x. So now let's move over to the exponential y is equal to 2x. So again, I'm just going to take points and I'm just going to reflect them about the identity line. Now, I'm going to pick that point, right? No, incorrect. That was a bad point. I'm going to start off maybe with this point. It looks like 1, 2. So x is -2, I found. Y was equal to 1/4. So this is 1/4, 2. Incorrect. Let me start over again. This point here, maybe I should write it down, is -2, 1/4. So that turns into 1/4 -2 on the inverse. This point here turns in, it is -1, 1/2. It turns into 1/2 -1. There. This point is 0, 1. It turns into 1, 0. This point over here, oh, now I have a point 1, 2, which is going to turn into 2, 1. Now this point here looks like it's 2, 4, so it's going to turn into 1, 2, 3, 4, 2. So this is, and I should flatten out a little bit more than that. I should be a little bit more careful. It looks like this. Okay? So now recall, so what is this? This is the function y is equal to log. My base here was 2x. These is how logs are looking. And by the way, I'm just going to draw a vertical asymptote here. So we had a horizontal asymptote at y is equal to 0 for the exponential. So for the logarithmic, again, right, we're going to have y is equal to, x is equal to 0 for a vertical asymptote. That was kind of hard. Kind of wiped. But let's continue on. I mean, most of our work here is done now. So what was my point? My point was a contrast of bases. So when the base is stuck between 0 and 1, we have this behavior here. When the base of an exponential function and of a logarithmic function is between or greater than 1, it'll behave like this. Now, there's going to be some commonalities. Identify the following characteristics of the inverse. Well, I'm going to start off with the left-hand side. So I'm just of the inverse of the log function, right, of the purple functions. So the left-hand graph, the domain looks like, well, what can x be? 0 to infinity. What can the range be? Well, the range can be negative infinity all the way up to infinity. My x-intercept of my inverse function is going to be 1. My y-intercept is going to be none. My asymptote of my purple function, well, there's a VA, the vertical asymptote, at x is equal to 0. Now, interestingly, I believe it's going to be the exact same. So we have two functions that are described the same way, right? The domain is 0 to infinity. This one might be easier to see, it's more pleasing to my eye. The range goes from negative infinity to positive infinity. The x-intercept, well, we have one x-intercept at 1. The y-intercept, there is no y-intercept. And the asymptote, still, we have a vertical asymptote at x is equal to 0. A lot of the same characteristics. However, what does this imply? The domain is positive. Notice that the domain corresponds to the x. In other words, the argument of our logarithms always have to be positive, no matter what case you're in. The range, what are the possible outputs of a logarithm? Really, they can be anything. And if you think in reverse and jump back to the exponential function, the exponent can be anything, right? Positive or negative. So let's move on. I think that's really great stuff. All right. The Richter Scale. Did you guys know that the Richter Scale is logarithms? And you may ask yourself, I'm always fascinated about earthquakes because it seems like an earthquake of 6 can cause damage. Or an earthquake of 7 causes a lot of damage. An earthquake of 8 causes a lot more damage. An earthquake of 9 is absolutely devastating. And I used to believe that the highest that the Richter scale went was 10. But that's wrong. What are Richter scales based on? They're based on logarithms.